Hello everyone. In the previous session we have learned what is a BST and we did some questions. Now in this session what we are gonna do is we are gonna talk about a special type of BST, that is AVL trees. So AVL trees are nothing but, you can say, a special type of BST, and whatever the nodes you will pass, let's say you are passing a number of nodes, what AVL tree will do is that it will create a balanced BST. It is AVL trees is nothing but self-balancing BST. It will create whatever the nodes you are passing. It will automate the process of creating a balanced BST. This is the work of a AVL tree. Whatever the nodes you are passing, it will take the nodes and it will make a automate process for creating balanced BST. Now you might get a doubt that what is the meaning of balanced BST. So balanced BST is nothing but a BST which has minimum height. Let's say that there are 4 nodes. Let's say that I am having 4 nodes. So I can build this 4 nodes something like this. I can build a BST of 4 nodes like this, or I can build a BST of 4 nodes like this. So in the first structure, you can see that I have created my BST in a skew format. The tree, whatever the tree I have created, it is in a skew format and it is going in a deep, you can say, not curve but depth. And you can see that here in the first structure, in the skew structure, the height is 4, and in the second structure the height of the tree is 1 2 3, so the height is 3. So this second structure will become my balanced BST, and the first structure is not a balanced BST, it is a unbalanced BST because it has more height. So a balanced BST is nothing but a BST which has minimum height, that is known as a balanced BST. Now AVL trees, what AVL trees will do is that whatever the nodes you are passing, it will perform some operations, it will perform some comparison, and using this comparison it will create a self-balancing BST. We don't need to give separate function to make our BST a balanced BST. Whatever the nodes you are passing, AVL trees will make some operations and it will create the BST balanced itself. We don't need to create a separate function to make our BST a balanced one. In the previous session, when we are constructing a BST, we have created basically our BST using comparison. If it is greater, put it on the right, Now my question is, if we use the approach, we have created, I think, a construct or create BST function. We have created in the first session, we have created you can say a function create BST. So in the create BST, what I am passing is, I am passing root and I am passing arrays. I am passing an array list and I am creating my BST using comparisons. Let's say that I am passing a sorted array 1 2 3 4. So what this create BST will do is that it will take array and it will compare. This is my first element and the second element is greater or not. If it is greater, then it will put on the right, and this same process will go on, and my create BST will create a unbalanced BST eventually, right? So this will create an unbalanced BST. And what I used to do, I used to create a balance function. In the second session, I have created a function called as balanced BST, and I used to pass this array, and I will take the middle index and I will call for the left part, and the right part recursion function call for the both and left and right part. This is what I used to do to create a balanced BST. Now instead of calling or writing different function, I am gonna create a new structure of BST, a new type of BST that is self-balancing. You don't need to write separate code for balancing. You just pass the nodes, my AVL tree will do some operations and it will give you a balanced BST. This is the basic working of AVL trees. What it will do is that it will automate the process of balancing. It will automate the process of balancing. This is the main work of a AVL tree. It will, whatever the nodes you are passing, it will take in and it will create a balanced BST automatically. You don't need to give external operations, you don't need to perform anything. It will take whatever the nodes, and it will perform operations and it will give you automate version of balanced BST. I hope you have understood what is the main working of a AVL tree. Now talking about its importance, talking about the importance of AVL tree, this concept which we are gonna learn is very important concept. You can expect this concept in product based companies, in interviews you can find it, but to be specific, the interviewer will not ask you to write the code of AVL tree, because the code part, the programming part of AVL tree is so huge, it's so big. So generally you can't write the AVL trees, you can't construct AVL trees, you can't write the whole code within 30 to 45 minutes. So interviewer don't ask you that, because the code is long. But what he will ask is, he will ask the concepts related to BST, AVL trees. He will ask the concept. Now we should be very very clear with the concepts. If we are clear, then 80% of our understanding of writing code is completed. So what we will do is that in this whole session we will talk about the concepts, and at the end I will show you the code. Okay, now we have understood what is AVL tree, what is a balanced BST. Now the question arises that why do we need a balanced BST? Why can't we perform our operations on a skewed tree? What is the problem in it? Now I have told you that a BST is a efficient data structure when compared to a general binary tree, only because of the operations which we perform is will give lesser time complexity when compared to general binary tree. Let's say that we are performing operations like searching, we are performing operations like adding, insertion and deletion. Now I have told you that the time complexity of performing these three operations is big of H. Right? Now I want you to just observe this thing. I have write the time complexity as big of H. I am repeating this, that I have written the time complexity as big of H. So can I say that for a given BST the time complexity is totally dependent on the height of the BST? Let's say that I am having a skewed BST. Let's say this is my BST, which are having 4 elements. Now I am performing search operation for this last element. So what I will do, I will recursively call, and my function call, my number of operations is n, and my time complexity will become big of n. Now here the total number of nodes are 4. So total number of performed operations in my skewed BST will become big of 4. So basically I am performing 4 operations. Very simple, right? Now what if the sample size increases? Let's say that n is equals to 10 to the power of 5. Now for this huge tree, there are n number of 5, 10 to the power of 5 nodes here, right? So for this skewed tree, I will perform big of n operations. That is nothing but big of 10 to the power of 5 operations. I need to perform 10 to the power of 5 operations. Can you think that how many operations? Let's say as n increases, the total number of performed operation in my program will get increased. Whereas if you compare a balanced BST, let's say this is my balanced BST, and this balanced BST generally comes in the average cases, and I have told you that for average cases the time complexity will become big of H, will become big of log n. Right? Now if my n is equals to 5, then my time complexity will become log of 10 to the power of 5, that is nothing but 5 to the power of log 10. So can you see that 5 to the power of log 10 is very much lesser than 10 to the power of 5? Because of this, because of the time complexity is totally dependent on the height of the BST. That is why we, in order to make the BST efficient, we always try to make our BST a balanced one. And this is why we have introduced the concept of AVL trees. I hope you have understood what is AVL tree, what is a balanced BST. And why do we need like a balanced BST? Because in order to create our BST efficient one, if we don't create a BST which is balanced, then what will happen is that it will have the time complexity big of n. And if you observe in binary trees, I have written the code and its complexity is also big of n. So what is if my tree is skewed? I am getting time complexity of big of n, and in binary trees my time complexity is also like big of n. So this big of n of BST and this big of n of binary tree both are same. Then what is the difference between it? So to create a difference, to make our code efficient, to make our BST efficient, we are gonna use the concept of balancing. And AVL trees are used to create self-balancing tree. We don't need to create any external program. Our AVL tree will take all the things in consideration and it will automate the process of creating a BST. So I hope you have understood AVL trees, balanced tree, and why there is a need for creating a balanced BST. Now let us talk about some more concept. So in AVL tree, or in general a balanced BST or a BST, how we can tell that whether the given BST, binary search tree, is a balanced one or not? How we can tell? So we can tell that whether the given tree is balanced or not based on a property of AVL tree, and the property is this one, that is calculate the left height for a particular node, calculate its left part height, calculate its right part height, and if you get the value, final value as -1 or 0 or 1, if you get any of these three values, then that particular node is considered to be a balanced node. And if all nodes are having only these three values, all nodes in a BST is having these three only values, either -1 or 0 or 1, then that particular BST is considered as a balanced BST. And how we gonna calculate? That is nothing but left height minus right height. For a particular node, we will calculate its left height and the right height, and if I got the value, if I got the resultant value for that particular node, if its left height minus right height is either -1 or 0 or 1, then that particular node is a balanced node, else it is not a balanced node. And if any of the given node in my whole tree is unbalanced, then I will consider my whole tree as a unbalanced BST. I hope you got the logic. Now let us try to analyze for each and every node its balancing factor. We call this thing as a balancing factor, and from the balancing factor we will analyze whether the given tree is a balanced one or an unbalanced one. From balancing factor we will analyze whether the given tree is balanced or not. Now let us try run this thing. So here for this leaf node, it doesn't have a left child, so the left height is 0, right height is 0, right? Now for this particular node, the left height is 0 and the right height is 0, so the balancing factor for this node is 0. Similarly for this node also the balancing factor is 0, and for this node also the balancing factor is 0. Now if you come up for this fifth node, it has one child on left, one child on right. It means that it has left height 1, right height 1, and the balancing factor is equals to 1 minus 1, that is 0. Similarly for this also, it has no left child, it is nothing but left height is 0 and right height is 1, so the balancing factor will become 0 minus 1, that is -1. Now here you can see that the left height is 2 and the right height is 2. Now for this particular root node, the balancing factor will become 2 minus 2, that is 0. So you can see that for the root node the balancing factor is 0, and for the secondary root node the balancing factors are 0 and -1. After that, for leaf nodes my balancing factors are, for all the leaf nodes balancing factor is 0. So I am getting either -1 or 0 or 1. Yeah, you can see that for all nodes in the structure 1 are either -1 or 0 or 1, and it is not exceeding beyond that. It is not having a value as -2, or it is not having a value as 3, something like that. It is not having those kind of value. The balancing factor are in between -1 to 1. So this structure is considered as a balanced BST because all the nodes is having balancing factor as 0 or 1 or -1. I hope you got the concept. Now if you observe the second structure, for this there is no left height, right height, there is no left node, right node. So the balancing factor will become left height is 0, right height is 0. So the balancing factor will become 0. Now you can see that for this there is no left child, so the height will become 0, and there is a right child, so right height will become 1, and the balancing factor will become 0 minus 1, that is -1. This is my balancing factor. Now similarly, if you observe this, the left height is 0 and the right height is 2, so this will give me -2 as balancing factor. Similarly, this is the left height is 0, for this the left height is 0 and the right height is 3, so 0 minus 3, this will become my -3 will become my balancing factor, and for this also my balancing factor will become -4. So you can see that my balancing factor for various nodes are exceeding the value of -1, 0, 1. It is beyond this. You can see that these three values are beyond this parameter, this parametric conditions. So if I am getting any of these values greater than -1, less than -1 or greater than 1, then that particular tree will become a unbalanced BST. I hope you have understood how we can tell whether the given tree is a balanced BST or not. We can tell that whether the given tree BST is a balanced BST or not based on a property, and that property is balancing factor. And the formula for balancing factor is that for a particular node calculates its left height and the right height, and if the resultant value gives you -1 or 0 or 1, that particular balancing factor, that particular node is considered as a balanced node. And if all the nodes in your BST are balanced, then and only you can consider that your whole tree is a balanced one, else it is not a balanced BST. I hope you have understood how we can tell whether the given tree is balanced or not based on balancing factor. Now let us talk about rotations. So in AVL trees we have a concept of rotations. So before going to like rotations, what is rotation and all those kind of things, let us try to build our BST. So here for this first number of nodes, first of all I will create my root node as 30. After 20 will come on its left and 10 will come on its left because the value is less. So this will become my structure, and for this 30 will become my root node and 10 will become my left, 10 will come on the left part, and 20 is less than 30, so it will come on left, and 20 is greater than 10, so it will come on right side, right? And for this third number of third values, third type values, 10 is the root node and 20 will come on the left side, and 30 is greater than 10 and greater than 30, so greater than 20, so it will come on the right side, 30 will come on the right side. Similarly for this fourth type values, you can see 10 will become a root node. After that 30 is greater than 10, so it will come on the right side, and 20 is less than 30, so it will come on the left side, right? This is the structure. And if you try to build the BST for this 2, then my BST will become 20 will become a root node, and 10 is greater than 30, so it will come on the right side, and 30 is greater than 10, so it will come on the right side, and 10 is less than root node, so it will come on the left side. Similarly the second value is also same, 20 will become my root node, 10 is less than, so it will come on the left side, and 30 is greater than 20, it will come on the right side. So these are the 4 different structures I will get. Now let us try to calculate the balancing factor for each and every given different types of BST. Here you can see that the values are same, but the arrangements of values is different, and because of this arrangement I am getting 4 different structures of BST, right? Now let us try to calculate the balancing factor for this 4 figures. So you can see that for this first figure, this is the leaf node, right, and it doesn't have any left child and right child, so the balancing factor is 0. And you can see that for this, left child is 1, left height is 1 and the right height is 0, so 1 minus 0, it will give me 1. And for this 30, the left height is 2 because the number of nodes present on the left side are 2 and the right height is 0. So what is my formula for balancing factor? Left height minus right height. Left height is 2 minus right height is 0, that is 0. 2 minus 0 will give me 2. So the balancing factor for 30 will become 2. Now for this second structure, for 20, the leaf node, there is no left height, right height, so it will become 0. And for this 10 node, it has some right child and left child is 0, so 0 minus 1, this will give me minus 1. And for 30, the left child height is 2, so this will give me 2 minus 0 because there is no right height. For this 30 node, there is no right height, but the left height is 2, so 2 minus 0 will give me 2. Now you can see that for this structure, the balancing factor of 30 is 2 and the balancing factor of 20 is left height is 0, right height is 1, so this will give me 1. And similarly minus 1, this will give me minus 1 and this will give me minus 2. Now for this, the balancing factor is 0 and for 30, the left height is 1, right height is 0. 1 minus 0, it will give me 1. Now for this 10th node, the right height is 2 and the left height is 0. So 0 minus 2, this will give me minus 2 as output. Now for this is a balanced structure, right? So for the root node, the balancing factor is 0. And for similarly, for 30, the balancing factor is 0. And for the root node, you can see that left height is 1, right height is 1. So 1 minus 1, this will give me 0. So this is a balanced BST, and you can see that the first structure, second structure, third structure, fourth structure, second structure, third structure, fourth structure. These four structures are unbalanced in its nature because I am getting some balancing factor value as greater than minus 1, less than minus 1 or greater than 1. So I need to change those values. What I can do? I have a clear vision, I have a clear idea of how my balanced BST will look like. Now what I will do is that I will rotate my BST in such a way that I should get my BST as a balanced BST, as a structure similar to my balanced BST. You can see that in the fifth figure, I got my balanced BST. So whatever the rest of the figures I am having, I will try to take those values and I will try to bend it over, rotate somewhat and try to make those structure similar to my fifth structure. This is my idea, and here comes the concept of rotation. So what I will do is that I will observe the balanced BST. I will observe the balanced BST and I will try to make the given balanced, I will try to make the rest of the 4 types similar to my fifth balanced, that is nothing but fifth type structure, which is balanced structure, right? This is the idea. Now let us talk about the first figure. So in the first figure, you can see that this is my balanced BST, unbalanced BST, and this is the balancing factor. Here the balancing factor is exceeding 1, it is greater than 1, and it is violating the properties of balancing factor. Okay, now what I will do is that I will make a pivot point. In physics we used to study, right, through from the perspective of pivot point, whatever the objects are rotating, it will rotate around it. And if you observe the doors also, doors has a pivot point, and from this pivot point the door will rotate like this. With respect to this pivot point, we rotate the door. Now what I will do is that I will make 20 as my pivot point and I will try to rotate this structure. I will try to make a right rotation. When I make a right rotation, this is the structure I am having, right? Now when I make a right rotation, my tree will become like this and 20 will come on the top, and when 20 will come on the top, the balancing factor will get automatically adjusted because 20 will become my root node. When I do a right rotation, 20 will become my root node, and this is what I want, because if I got the root node as 20, the tree will become balanced in nature, right? I hope you got the logic here. why I am doing right rotation, why I am choosing 20 as my pivot point after rotating right. With respect to pivot point, I am rotating it and performing a right rotation, and when I perform a right rotation, the whole tree will rotate, and when the tree rotates, 20 will come in the middle, and when 20 will come in the middle, 20 will become the root node, and this is what exactly I want. So what I will do is that I will perform a right rotation, and when I perform my right rotation, my tree will become something like this. 20 will become in the middle, 10 will come on the left side, and 30 will come on the right side, and 20 will become a root node, and you can see that it become a balanced BST. So what I did is I have rotated my whole BST through a pivot point, and pivot point will remain the same position, but all the corresponding nodes which are along it will get rotated. Okay, this is what I did, and 20 become my middle node, basically root node, and 10 came on the left and 30 came on the right side, and my whole BST gone through from unbalanced to it become a balanced BST. So I hope you have understood. Now let us understand the second thing. In the second diagram, I will make 20 as my pivot point. After it, I will try to make a left rotation. I will try to make 20. I will try to take 20 on top, and after taking 20 on top, 10 will come down. When I do a left rotation, perform a left rotation here, 20 will come on the top and 10 will go down, right? So this is what my structure will become. When I perform the left rotation, what will happen is that 30 will remain on the top. After 20 will come here and 10 will come underneath them. Now this is my pivot point. So what I will do is that after performing left rotation, and again after this I will perform the right rotation again. Now you can see that this is very similar structure to this. Both structures are same. 1 and 2 structures are now same. So when I perform right rotation, 20 will become the root node. Finally I will get a structure like this. Here you can see that I am performing 2 rotations. First of all, I have performed left rotation, and because of left rotation, the 10 came down and 20 goes up. Now after that, I have performed right rotation, and when I performed right rotation, my 20 will become my mid value, my root. After 10 came on the left, 30 came on the right. This is what I am doing. Now one more thing you need to keep in your mind, that when we perform rotations, two rotations, we consider that as a unit rotation. We don't consider it as a 2 separate rotations. We will consider as a unit rotation. We will consider this left rotation and right rotation as a single rotation in itself. This is a concept. Basically you need to keep this in your mind. Now let us talk about this structure. Here I will make again 20 as my pivot point, and if I perform left rotation, if I do a left rotation, then 20 will become my root node, and 10 will come on the left and 30 will come on the right. And one more thing is that if you observe logically, that for this third structure, if I perform a right rotation, then what will happen? 20 will come on the root side, but 30 will come on the left side. That is totally wrong. It will become not a valid BST. It doesn't follow the properties of BST if I perform a right rotation. That is why I need to perform my left rotation, because it has to satisfy the property of BST, and at the same time my 20 nodes should become the root node. So what I will do is that I will perform a left rotation here. I will perform a left rotation, and 20 will become my root node, 10 will come on the left side, and 30 will come on the right side. So this is my structure, right? So what I am doing is I am performing left rotation, and when I perform my left rotation, the 10 value will come on the left side, and 30 will come on the right side, and 20 will become my root node. And this structure become a balanced structure. Now for this third diagram, I will take this 20 as the root node, and I will perform the right rotation, and when I perform the right rotation, 20 will go up and 30 will come down, and this structure will become similar to this. First of all, I have performed right rotation. After 20 will go up and 30 will come down. So this is what my structure will become. Now after this, what I will do is I will perform the same rotation as left rotation, and when I perform the left rotation, my diagram will become like this. I hope you have understood. And one more thing is that if I have n is equals to 3, then the total number of this is a formula, if the total number of, then the total number of BSTs that can be formed from n nodes is n factorial. Here you can see that the 3 factorial is 6, and we got 6 different diagrams, 1, 2, 3, 4, 5, 6. So if the number of total number of nodes are n, then the total number of BSTs formed out of is n factorial. This is a general formula, and I hope you have understood why I have chosen 20 as a pivot element, because I wanted to make 20 as a root node, and with respect to the pivot element I performed all my rotation and made my 20 as the root node, and when I made the 20 as the root node, my BST became itself you can say a balanced BST. This is the concept of rotation. And one more thing is that all the rotation, you have to keep this in mind, all the rotation that we generally perform is only on 3 nodes, right? So let's say you have a huge tree, so we will check at what point the balancing factor is disturbing, and from that point we will take 3 nodes and we will make one element as a pivot element, and with respect to this pivot element we will perform, and whatever the rotations is happening, that will happen only on 3 nodes. We won't take 10 nodes and perform rotation, it will become so complex. We only perform rotation on 3 nodes, whatever the tree might be, whatever the size of tree might be, we only perform rotation on 3 nodes only. We will break it down, we will only consider these 3 nodes and we will rotate this. I will explain you how a BST is formed in diagrammatic representation. I will show you. Now let us talk about the cases. So what are these cases? Now talking about cases, in AVL trees we are having 4 cases, and you need to remember these 4 cases. You need to basically by heart this 4 cases. So what we will do is that at each and every step we will check whether the balancing factor is disturbed or not, and if it is disturbed, then at what case it is getting disturbed, and after finding which case we got, we will perform its corresponding rotation, right? So what are the steps we will follow when creating a AVL tree? First of all, we will insert node. Whatever the node it is given, we will insert that node. After that, we will check if the balancing factor is disturbed or not. If it is disturbed, then because of which case it got disturbed. After finding the case, we will perform its corresponding rotation. These are the 3 steps we will follow. First, I will insert the node, and after inserting the node, I will check for these 3 nodes what is its balancing factor. If the balancing factor is correct, if it is not violating the properties of balancing factor, then I will continue to add for the next element. If the balancing factor is disturbed, then I will check due to which case the balancing factor got disturbed. And when I found out the case, oh, because of this case my balancing factor got disturbed. So for each and every case I have a corresponding rotation. I will perform that rotation, and when I perform that rotation, my tree will become balanced, right? Now let us try to make this. So here this is my AVL tree, and I need to add 10. So you can see that 10 is less than 30, so it will come on the left side, and 10 is less than 20, so it will come on the left side again. So my tree will become 30, 20 and 10. And here you can see that the balancing factor is 0. The balancing factor is left height is 1, right height is 0. So it will become 1 minus 0, that is 1. And here balancing factor will become 2 minus 0, because the left height is 2 and the left height is 0. So this will become 2. So here you can see that the balancing factor got violated. And the balancing factor got violated because I have inserted 10. And at what position I have inserted? I have inserted my 10th node on the left side, left elements left. So you can see that first of all I have on the left side there is a secondary root, and for the secondary root I have inserted the new element on its left side. So left's left, this is the case of LL case. So if I got, when I insert element on the left side, because of inserting on the left side, if this is the case, then what I will do is that I will perform a right rotation. I will perform right rotation and after performing right rotation, my tree will become balanced. So this is the tree I am having, right? 30, 20 and 10. So what I will do is I will perform right rotation. When I get LL case, I will perform right rotation. You have to keep this in mind, that when we get LL case, we will perform right rotation. And when we perform right rotation, after rotation, 20 will become my root node, and 10 will become my left part, and 30 will become my right part. And if you observe, the balancing factor is 0, 0, and here the left height is 1, right height is 1, so this will become 0. Here the balancing factor is satisfied, hence the tree is balanced. So I am summarizing. I am having 30 and 20 node. Now I need to insert 10, and when I inserted 10, my balancing factor for the top node, for my root node, got disturbed. And I have seen why it got disturbed, because I have inserted element on the root left part, and for the secondary part, and again I have inserted for the secondary root left part. It means that left, because inserting 10th new node on the left side, my old tree got disturbed. My old tree become unbalanced, and because of this, inserting the left node left part, because of this my old tree become unbalanced, and this is a case of LL case. I have inserted my new node on the root left part. Because of this, this is a case of LL case, and whenever I get LL case, I will perform right rotation. And after performing my right rotation, my old tree will become a balanced BST. Now let us talk about, this is the first case. The first case is LL case. Now let us talk about LR case. That is, let's say this is my AVL tree and I need to insert 20. So what I will do is that this is my 30, right? So 20 is less than 30, so it will come on the left side, and I am having 10, and 20 is greater than 10, so it will come on the left side. Now let us check the balancing factor. The balancing factor for 20 is 0, and the balancing factor for this 10 node is left side 0, right side 1. So 0 minus 1, this will give me minus 1. Now for this, the left height is 2 and the right height is 0, so 2 minus 0, it will give me 2. Here the balancing factor got disturbed because I have inserted a new node on the left node's right part. When I inserted the new node on the root node left node's right part, because of this my old tree become unbalanced. And when I get a LR case, what I will do is that first of all I will perform left rotation. After that I will perform a right rotation. So what I will do is that first of all I will perform left rotation. So when I perform a left rotation, my 20 node will come on the on top and 10 will go down. So my tree will become something like this: 30, after that 20, after that 10. Now if I observe, the balancing factor is 0, 1, after that 2, right? And after this what I will do is that I will immediately perform right rotation. So when I perform right rotation through this pivot element, what will happen is that I will get a balanced BST. After performing right rotation, 20 will come in the middle, 10 will come on the left side, and 30 will come on the right side. So here in LR case I am having nodes, and I have inserted my new node on root node left side, and this left side, whatever the nodes I am having, this node's right side, it means that on the left and right side. Because of adding this new node on the LR side, this is a LR case. And whenever I get a left right case, first of all I will perform left rotation, after that I will perform my right rotation. After performing this, my old tree will become a balanced BST. I hope you have understood. Now in the third case, let us say the third case is RR case. Let's say this is my tree, I am adding 30, so 30 is greater than 10, so it will come on the right side, and again 30 is greater than 10, so it will come on the 20, so it will come on the right side again. So if I calculate the balancing factor is 0, left height is 0, right height is 1, so 0 minus 1, it will give minus 1, and this will give minus 2. Here you can see that the balancing factor is disturbed. Why? Because of inserting a new node on right part. right part. Because of inserting this, my whole tree become unbalanced, and when I inserted a new node on right side, this is a RR case, and whenever I get a RR case, I will perform left rotation. So what I will do is that I will take this unbalanced tree and I will perform a left rotation, and when I perform my left rotation, my whole tree will get rotated like this, and I will get a balanced BST. After rotation, after left rotation, my tree will become 2 will become my middle element, 10 will come on the left and 30 will come on the right. So this is a case of RR case. Whenever I get a RR case, I will perform left rotation. Now let us talk about the last case, that is RL case. So in RL case, let us say that this is the AVL tree I am having, and I am inserting 20. So this is 10 after 30. So you can see that 20 is greater than 10, so it will come on the right side. After that, 20 is less than 30, so my 20 will come on the left side. Here you can see that right's left side, and if I calculate the balancing factor is 0, 1 and minus 2. So here you can see that my balancing factor got disturbed because inserting an element on the right side and the secondary root left side. Because of this RL case, my whole tree become unbalanced, and whenever I get a RL case, what I will do is that I will first of all perform right rotation, and after performing right rotation, I will perform left rotation, and after this whole thing, I will get a balanced BST. So what I will do is that I will perform first of all I will perform right rotation. This is the tree, right? 10, 30 and 20. So first of all, I will perform a right rotation, and when I perform my right rotation, 20 will come on top and 30 will go down. So my tree will become, after right rotation, my tree will become 10 will come on top, after 30, after 20, after 30 will come down. Now after this, I will perform my left rotation, and after performing my left rotation, my whole tree become like this. 20 will come in the middle, 10 will come on the left and 30 will come on the right side. So 20, 10 and 30. So this will become my balanced BST. So whenever I get a RL case, I will perform right rotation after left rotation. Let me summarize that. If I got LL case, adding a new node on the left side, I will perform what in LL case, what I will do is that I will perform right rotation. I will perform, you need to remember this, right? After, whenever I get a LR case, first of all I will perform left rotation after right rotation. Whenever I get a RR case, I will perform left rotation. And whenever I get RL case, first of all I will perform right rotation after left rotation. This is what I do. On these 3 nodes, based on the condition, I will perform the corresponding rotation. Whatever the rotation is needed, I will do that. So these are the 4 cases, and all over BST, whatever the nodes might be, we only get these 4 conditions, and based on the cases, we will perform the corresponding rotations. Now let us talk about, we have seen for the small trees. Now what if my whole tree is big? What will happen after performing LL? So in LL case, when I perform in LL case, what I have to do, I need to perform right rotation. I will perform right rotation. So when I perform right rotation, this will become my root node, right? So B will become my root node, and this A will come on the right side. So this A will come on the right side, and whatever its children the A is having will remain the same. So A's children will remain on the same right. So A's right will remain the same. After B left child will become C, right? C will come on the left, and whatever the C's children having, those will not get disturbed. So C's left will remain same, after C's right will also remain same. But this B's right will come on the A's left side. So B's right will come on the left side. So this is what will happen when we perform LL case on a huge tree. Now I want you guys to perform RR case on your own. This is quite opposite. RR case is quite opposite to LL case. whatever the values you are getting, you will get this in a reverse order. That's all. I want you to perform LL case for this tree. Now let us talk about LR case. Now for this huge tree, in LR case, what I have to do, first of all, I have to do left rotation. After that, I need to do right rotation. So what I will do is that first of all, I will perform left rotation. When I perform my left rotation, C will come on top and B will go down. So A will remain the same. A and its children will remain the same, and C will come here, and C's right part will remain the same, but B will come on its left part. So B will come on its left, and B's left will also remain the same. And here you can see that I am only missing C's left part. So this C's left part will come here. So C's left part will come here. This is what left rotation will do. Now after that, I need to perform right rotation, right? Right rotation is nothing but RR case. So when I perform right rotation, C will become my middle element. So C will become my middle element, and C's right part will become my A. C's right will become A, and whatever A's children is having, it will remain the same. So A's right part will remain the same, and this C's left part will get occupied by B node, and here B's left part will remain the same, BL, and here I will get CL. Now this C's right part will come in this here. C's right part will come on A's left side. So after right rotation, this is what will happen for my tree. For my old tree, this is what the structure, and this is a balanced structure. So I have showed you LL, and basically this is RR rotation. To be specific, this is RR rotation, and I have shown you LR rotation. Now you can do RL rotation on your own, right? Take this diagram and try to perform the RL rotation. So in RL rotation, what will happen is that the BC will like rotated, and after instead of performing RR, what we will do is that we will try to perform this, and finally I will get this structure, right? LL. Basically, after performing right rotation, what I will do is that I will perform left rotation, which is very similar to this. This is what I did, right? So I hope you have understood, and I want you guys to perform RL rotation for this particular tree structure. I want you to perform RL on this particular structure. So up to now we have seen what is a AVL tree, why we use it, what is the concept of balanced tree, balancing factor, types of rotations, 4 types of rotations, and we have studied 4 types of cases, and based on cases we will perform different rotations, right? I hope you have understood what are these cases, and after that what are the corresponding rotations that we generally perform. Now let us try to build our own AVL tree for this all values. Now here these are the how many elements I am having: 1, 2, 3, 4, 5, 6, 7. So here let me not take this, because I don't want to make my huge AVL tree, because this will take long process. I don't want to make my videos so long. So here what I will do is that I will make my AVL tree only for the 6 elements. So what I will do is that I will iterate through each and every element, and as I iterate, I will make that as a root node, and I will compare for each and every case, for each and every step. I will check the balancing factor. If the balancing factor is satisfied, then and only I will include another element into my BST, into my AVL tree. Else what I will do is that I will perform the rotation based on the corresponding case. Now let us start our building BST process. So first of all, 40. So I will make, in the step 1, I will make 40 as my root node. Here the balancing factor is 0. Okay, satisfied. So I will go to the second element, and in the second element here you can see that 40 is greater than 20. So 20 will come on the left side. So in the second step, 40, this is my root node, and 20 will come on its left. Now check balancing factor. Balancing factor for this thing is 0, and here balancing factor left height is 1, right height is 0. So balancing factor will become 1. Here both are satisfied. If both are satisfied, then I will go to my next step. For this third step, I will add 10. So 40 and 10 is less than 40, so it will come on the left side. 20, and again 10 is less than 20, so here it will come on the left side. Now check balancing factor. The balancing factor for this is 0, and here for this is 1, and for this is left height 2, right height is 0. Now balancing factor got disturbed. If the balancing factor got disturbed, what I will do is I will check what case this is. Here, because of inserting left side, this is LL case. If I got LL case, what I will do, I will perform right rotation. I will perform right rotation. So what I will do is that I will perform right rotation, and after performing right rotation, my old tree will get converted, and 20 will come on left. So 20 will come on middle, and 10 will come on left, and 40 will come here. This is what I do. Right now here you can see that the balancing factor is 0, 0, 0. Yeah, my tree is balanced now. So I will iterate through the next element. Here I will iterate to 25 and add 25. This is my step 4. Here you can see that 20 is my root node, and 10 is my left part, and 40 is my right part. Now 25 is greater than 20, so it will come on the right side, and again 25 is less than 40, so 25 will come here. Now here you can see that the balancing factor is 0, 0, and for 40 the balancing factor is 1 minus 0. Left height is 1, right height is 0, so this will become 1. And here for 20 node, the balancing factor is left height is 1, and the right height is 2, so 1 minus 2, so this will give me minus 1. Yeah, balancing factor is satisfied. So I will add my next element. I will go to my 5th step and add next element. So 30 is my next element. So here this is my structure, right? 30, 20, 10, 40 and 25. Now 30 is greater than 20, so it will come on the right side, and 30 is less than 40, so it will come on the left side, and 30 is greater than 25, so it will come here. Now check the balancing factor. So for 30 the balancing factor is 0, and for this structure left height is 0, right height is 1, so 0 minus 1, so this will give me minus 1. And for this the left height is 2 and the right height is 0, so for this the height is 2, and you can see that here for 10 the balancing factor is 0, and for 20 the balancing factor is 1, left height is 1 and the right height is 3, so 1 minus 3, so this will give me minus 2. Here you can see that the balancing factor got disturbed. Now if the balancing factor got disturbed, here you can see that in the two positions here and here my balancing factor got disturbed. Now I will check what is the first value at which my balancing factor got disturbed. Here this is my first value, so I will consider these 3 nodes, and because of inserting a new node on right side left part, this is a RL case. So if I get a RL case, what I will do is that I will perform right rotation after left rotation. So what I will do is that first of all I will perform my right rotation. So when I perform my right rotation on 40, 25, 30, these 3 nodes, my tree will become like this. So when I perform a right rotation, I need to perform a right rotation. My 30 will come on top and 25 will come down. So my tree will become something like this: 20, 10, after that 40, after that 30 will come on top. 30 will become 30 will come on this side. Let me erase this. Okay. Continuing. So 30 will come on this side, 30, after 25. After this I need to perform my left rotation. On this tree I need to perform my left rotation. So when I perform my left rotation, my old tree will become like this. These 3 nodes will come in the middle, and 30 will become the middle node. So 20, 10 and 30 will become the middle node, and 25 will come on its left and 40 will come on the right side. Now check the balancing factor: 0, 0, 0, 0, and here 0 minus 2, so this will become minus 1. Here the whole structure balanced, the whole balancing factor for each and every node is balanced, so my whole tree is balanced. So here after like whole tree is balanced, I will go to my sixth step, so adding 22. So this is my 20 node, right? 20, 10, 30 and 25. I hope you are with me. I hope you have to listen and draw the diagram with me. When you understand this, you will understand how a AVL tree is being created, right? After 40. Now what I will do is that I will add 22. Here you can see that 22 is greater than 20, so it will come on the left side, and 22 is less than 30, so it will come on the secondary root right left side, and again 22 is less than 25, so it will come on the left side. Now check the balancing factor. The balancing factor is 0, and after that the balancing factor is 1, and the balancing factor for this thing is 2, the left side is 2 and the right side is here 0 and 2 minus 1, so this is 1, and after that here you can see that the balancing factor is 0, and for this 20 node the left side is 1 minus the right side is 1, 2, 3, so 3, so this is minus 2. Now here you can see that the balancing factor got disturbed. Now you can see that because of adding a node on the root nodes right, left, so this is a RLL case, and we don't have a case called as RLL. So what we will do is that we will ignore this. And what I will do is that I will perform right rotation first. In RL we used to perform, you can see that in RL we will perform right rotation, after it will perform my left rotation. So what will happen is that 20 will become my root node, after 10 will become my node. After what will happen is that when I perform 20 right rotation on this two nodes, 25 will come in the mid and 30 will come on the right side, and 22 will remain the same. So what will happen is that 25 will become my root node and 30 will come on the left side, and 22 will become my left child. Now this 40 will come on the right side. Now after this I need to perform my left rotation. So I will perform the left rotation, and when I perform the left rotation on these three nodes, my 25 will become my middle element, right? So 25 will become my middle element, and 20 will come on the left side. 20 will come on the left side, and this 10 will come on the 20's left side, and 22 will come here, and after that 30 will come here, and 40 will come like this. Now if I check the balancing factor for this whole structure, 0, 0, 0. Here the balancing factor is 0. Now for this the balancing factor is minus 1. If you observe for the root node, the balancing factor is 2 minus 2, that is 0. For this whole structure my balancing factor got same. So for this structure, for this AVL tree, 40, 20, 10, 30, 22, right, these are the different nodes, right? 1, 2, 3, 4, 5, and here I think I am missing one more node. Yeah, 25. Here 25. So for this 6 nodes, my final AVL tree function will give me this: 20, 10, 22, 30, 40. So this is what finally I will get. This is what my AVL tree will give me. This is what my AVL tree is, right? AVL tree will give me this structure, final structure for this whole node. I hope you have understood the overall working process. At each and every step I am checking balancing factor. If the balancing factor got disturbed, then I am checking at what case, for which case it is getting disturbed, and I will, after finding the case, I will perform the corresponding rotations. Each case will have a rotation, right? So I will perform the corresponding rotations, and after it finally I will get my structure. I will get my required AVL tree. So this is the whole concept of AVL tree. Now let us see the code of a AVL tree. Okay, so let me explain the code briefly. Just I will explain what is the code and how it is working briefly, and I will give you the code also in the description. I will give you the code, but here what I am doing is, first of all, I have created a class AVL node, and this AVL node will represent a single node in my whole AVL tree. What are the properties this particular node will store, this class will represent. After that, what I am doing is I am creating a AVL tree class to represent my whole AVL tree, and in this I am creating my roots, I am calculating the height, and I am calculating whether the tree is balanced or not. Now after it, I have created function for right rotation, I have created the function for right rotation, left rotation, whatever. For right rotation and left rotation, I have created two different functions. Now after it, I am calculating whether the tree is balanced or not. Now after that, I have created a insert function. In this I will pass my node and key value, and as I add my node, I will check whether it is a balanced or not, and this is where I am checking my 4 conditions: condition 1, condition 2, condition 3. And if the tree is not balanced, if the balance is greater than 1 and overall tree balancing factor is not like within the given parameters, now I will call, based on the tree, I will call the corresponding function. I will call the corresponding rotation function, and after calling the rotation function, finally in the insert program I will return the root, because my return parameter of root is a node, so I will return node. Now after that, here in the AVL delete function, basically I am deleting the node from my given tree. So my user will give me root node and tree, and basically this is as same as BST. In the BST I have shown you what I am doing in deletion operation. This is the same code here. So I am basically deleting the element. Now after that, after deletion I am searching, I am performing the search operation, and after that I have created a pre-order sequencing, and in the main program I have constructed this AVL tree, and I am calling the AVL tree function, I am calling the AVL tree class and the AVL tree insert function. After that, basically I am printing my pre-order. This is what I am doing. So in the insert is the same. Insertion is the important thing, and if you understand the insertion, the whole thing got completed. Deletion is as same as BST, and insertion is also as same as BST. Now in the insertion, what I am doing is I have created the rotation functions, and in the insertion function I am checking for each and every node its balancing factor, and after checking the balancing factor I am checking at what case the balancing factor is getting violated. Based on the case I am performing the corresponding rotations. So this is what my whole AVL tree function will do. I hope you have understood. Now up to now we have studied the complete binary search trees, and we have completed complete binary trees concept. Now we will move to our next concept, and the name of the concept is heaps. So with that being said, I will see you in the next chapter.